arc length in 3D, and the unit normal vector. Consider a curve in three-dimensional space, where, say, the starting point is over here at t equals a, and the end point is over here at t equals b. And we want to find the length of this curve, that is the arc length, from t equals a to t equals b. Well, as we know in calculus, when we want to find a measure, such as length, area, volume, etc., we start with a simple geometric shape, and we're going to approximate it. So the simple geometric shape we're going to use to approximate a length is the three-dimensional Pythagorean theorem. So by the Pythagorean theorem, in three-dimensional space, we know that each of these segments over here has the length given by the square root of delta x squared plus delta y squared plus delta z squared. It's the length of one segment, one portion of the entire graph. Now, if we want to find the entire length, there are two things we need to do. The first thing is we need to let our deltas, x, y, and z, all go to 0, which will give us the following. One very small line segment would have the length dx squared plus dy squared plus dz squared. And then the second thing we need to do would be to add all of these really tiny line segments together. So maybe one there and another one. Imagine they're infinitesimally small. And of course we know that in calculus, to add things together, add very small things together, we do that through an integral. So this is the arc length, but not really of a form that we can use. So let's change the form slightly. We'll do a little bit of algebra here. And let's factor a dt squared out of each of these pieces, giving us dx over dt squared plus dy over dt squared, and then dz over dt squared. And all of these things, each one of these pieces, times dt squared. Let me fix this one little piece here. I put my squared in the wrong place. So out here like this. So each of these pieces we have factored out a dt squared, but I can pull that outside of my square root, giving us dt outside. So this is how we find the length of the arc from t equals a to t equals b. If you remember from Calculus 2 when we did parametric equations, it's the exact same thing, we just didn't have the dz dt. But now, if we consider r of t to be the vector x of t, y of t, and z of t, meaning that r prime of t is the vector x prime of t, or dx dt, comma y prime of t, comma z prime of t. Then we can see that our arc length right here is the integral from a to b of the magnitude of r prime of t dt. Right? Because the magnitude of r prime of t dt, that is just the magnitude of r prime of t, is the square root of x prime squared, I'm going to leave off the t for the sake of space, plus y prime squared plus z prime squared as well. Just like that. So here is our arc length in three-dimensional space. Now we can also talk about an arc length function. So let's consider r of t equals f of t I plus g of t j plus h of t k, or x I y j z k, on the interval a to b, where r prime is continuous and the curve is traversed exactly once from t equals a to t equals b. So we're not going back and forth on the curve. Then the arc length function s of t is given by s of t is the integral from my starting t a to some random t of r prime of u magnitude du. So an accumulation function starting at a and going to some unknown value of t, or any value of t on my interval. And then because we have t in our limit, we put our dummy variable of u in our integrand. So this is the arc length function. A quick note that ds dt by fundamental theorem of calculus is going to be the magnitude of r prime of t, or ds equals the magnitude of r prime of t dt. Now we may use this a little bit in this chapter, but this will become important when we get to our very last chapter. We do something called line or curve or contour integrals depending on where you're from. Let's do an example here. Let's find the length of r of t equals cosine t sine t comma t from the point 1, 0, 0 to the point 0, 1 pi over 2. So one thing to note before we start is that right here, this is t equals 0. Right? If t equals 0, we have the cosine of 0, 1, sine of 0, 0, and then 0. And this back point we get when t is pi over 2. So cosine of pi over 2 is 0, sine of pi over 2 is 1, and then pi over 2. So those are going to be our limits. So the length of the arc, and I could put s here if I wanted to, but I'm going to put L, is the integral from 0 to pi over 2 of the magnitude of r prime of t dt. Okay, well we need r prime of t and then we need the magnitude. So r prime of t is going to be negative sine of t, cosine of t, then 1. The magnitude of r prime of t is going to be the square root of sine squared plus cosine squared plus 1 squared, which is going to be the square root of 2. So our arc length is the integral from 0 to pi over 2 of magnitude of r prime of t, which is always root 2, doesn't matter what the t value is, dt. And then we can do our antiderivative pretty easily. We get root 2 times t from 0 to pi over 2. Plugging in the top limit, we get pi times root 2 over 2. Plugging in the bottom limit, we get 0. Let's do one more definition for you and with a little bit of information. So let's have a curve here in space, defined by r of t. And recall that t of t, our unit tangent vector, we define to be r prime of t over the magnitude of r prime of t. So we have one unit tangent vector. Now, there are many orthogonal vectors to this vector. Here is simply one of them. To help you think about it, think about at this point right here, we could rotate 360 degrees around r of t, and we'd have an infinite number of vectors that are normal or orthogonal to the unit tangent vector. We call the principal unit normal vector, or simply the unit normal vector, n of t, which will equal t prime of t over the magnitude of t prime of t. So clearly this is a unit vector. But how do we know that n of t as defined is orthogonal to t of t? It's pretty straightforward. Since t of t has a magnitude of 1 always, because it's a unit vector, we know that t prime, big T, dot big T equals 0. And we saw that in a previous video. Which means that big T prime is always going to be perpendicular to big T. And then we normalize it to make it have a magnitude of 1 by doing this down here. So let's do one example with that. Let's find the unit normal vector big N for r of t equals cosine of t, sine of t, comma t. Well, we want to start by finding big T of t, which is going to be r prime of t. So I'll change my notation here. We're going to have negative sine of t, cosine of t, 1, over the magnitude of r prime of t, so the square root of sine squared plus cosine squared plus 1 squared. So again, that's going to be r prime of t, or the magnitude of r prime of t. Which is going to be 1 over the square root of 2 times negative sine of t, cosine of t, 1. Now we want to find n of t, which is going to be big T prime. So I start there. So big T prime is 1 over root 2 times negative cosine t, comma negative sine t, comma 0, all over the magnitude of t prime of t. So it'll be the square root of 1 over t times, let me go back and make this a little bit clearer for us. We're going to do, I need to give myself a little more space, and I'm going to distribute this 1 over root 2 inside here. Before I do it, it's going to be 1 over root 2 times the negative cosine of t squared, so I don't really matter if I have the negative sign there, and then plus 1 over root 2 times the negative sine over t squared. But once again, the negative is going to cancel out, so I don't need to put the negative sign there, plus 0 squared like that. So we're going to get, up top we have 1 over root 2 times negative cosine of t I, and I'll go back to this notation, and then minus 1 over root 2 sine of t j. And I go back and forth just to make sure that you remember that these two versions are equivalent. And then I need to find the magnitude of this bottom part. Well, let's see what the magnitude of this bottom part is. So we're going to have 1 over root 2 squared, so 1/2, times cosine squared, plus 1 over root 2 squared, 1/2, times sine squared, and then all square rooted. So put it down here. So we'll get negative 1 over root 2 times the cosine of ti minus 1 over root 2 times the sine of tj, all over the square root of 1/2, or 1 over root 2, which of course will simplify for us down to negative cosine of ti minus the sine of tj. And this will be our unit normal vector. And it's pretty easy to show that the magnitude of this equals 1.